We are here to present our work supporting SENÇOTEN language documentation efforts with automatic speech recognition. And most of the team are from the National Research Council of Canada, and we also have partnered with the indigenous community. So before we talk about the detail, let's see our team. So we have a team working at the National Research Council of Canada on Canadian Indigenous language revitalization, and we have a long history working on it. The recent progress is like we started a big project in 2017, then followed by another big project more recently. And about myself, maybe I'm kind of different from most of you here. I don't have any linguistic background. So I did my PhD in speech techniques for low resource languages and for healthcare applications from the Chinese University of Hong Kong in Hong Kong. So I'm new to Canada and I have little knowledge about the indigenous language before I joined the NRC. And in this paper, we want to present a methodology or pipeline that will minimize the requirement of linguistic knowledge when we work on indigenous languages. So we also have partnership with the school board, which provide education services and SENÇOTEN language revitalization programs to over 400 learners in the territory. And one of the co-author is a language educator and developer for the SENÇOTEN language, and he has worked on that for a long time. So let me talk about the background and motivation. So we are now at Computer 8, and about automatic speech recognition or speech to text, there has been a lot of focus previously, but why we should talk about it again today? So here is a brief introduction about the evaluation or history of ASR, or automatic speech recognition. Oh, sorry. Yeah, I've gone over several pages. Yeah. Sorry for the reminder. Oh, I will finish it. Language documentation efforts with automatic speech recognition. And we are from the National Research Council of Canada, and we have a long history of working with the indigenous communities for language revitalization. So here is the team. So most of us are from the NRC. About myself, I'm also a computer science background. I have little knowledge about linguistics and about the languages. So in this work, we want to try to propose a pipeline that minimizes the requirement of linguistic expertise when working with the languages. So we also have a partnership with the school board, and one of the co-author of the paper is an active language educator. So that's where we stop. So I will focus on this. So now we are in Computer 8, and there have been a lot of work on automatic speech recognition in the previous conference. So why we are still talking about this today? So this is a brief introduction about how ASR progressed over the past decades. So maybe in 2000, like 25 years ago, we are in the era of statistical model, which is GMM, HMM. It requires a lot of stages. I will show it later. And later in 2010, we have the hybrid model, which brings hybrid deep neural network into the pipeline. Later, we have the end-to-end model, and now we are in the new era of the speech foundation model. So this is how it looks like 25 years ago. It is like a very complicated system. At that time, we don't have GPUs. So we have to construct separate models for acoustic part, for the language part, and we also have to have a pronunciation model or a dictionary to model all the words. Each of the parts takes a lot of knowledge and efforts. And with the limited availability of data in indigenous language, it is quite challenging. So later, this is when deep learning comes. So we have the deep neural network integrated in the pipeline. It replaces the Gaussian mixture model, but the overall architecture is still complicated. We have to do multiple pass work, and it requires a lot of knowledge. And like 10 years ago, there's a trend in ASR to shift from the hybrid approach to end-to-end approach. By end-to-end, the ultimate goal is to just we input the audio and we have a model, it's a huge black box, then we have the text come out. It looks good, it sounds good, but there's a cost for it. To train the huge black box well, we need a lot of data. And that's one of the key challenges in indigenous languages. We don't have that much data. So it still stuck if we in this era. And now we're in a new era with the speech foundation model that comes like in 2020s. And nowadays, maybe every month or sometimes every week, we have some newer architectures or newer configurations. So for speech foundation models, it's more like a huge knowledge base. It learns from most of the speech foundation models, it learns from the audio only. So it tries to encode the linguistic and the acoustic features inside its parameters. And we can fine-tune it on the downstream task. And one of the major downstream tasks is automatic speech recognition or speech to text. But it can do more than that. And this helps to solve the challenge that we have limited parallel data. So we kind of like we have a very expert system inside, and we need to tune the system or teach the system to do our task. So here are the three major and most popular speech architectures of the speech foundation models, or we can just call it SFM. So basically, they share a similar structure, like it uses a transformer backend. The transformer has a mechanism called attention that changed the research field like 10 years ago. And for Whisper, it is kind of different, like it also has a decoder. And for pre-training, it's trained on label data. But for the Whisper, other than Whisper, for the Wave2Vec2 or Hubert, it is trained on audio only. And as our language is very different from the mainstream language, we don't expect it to work well or don't expect it to work that well. But later we prove that actually for speech, it shares something in common. So here is an overview of how the ASR performance progressed in the past maybe 3 decades. So this is a statistical model. This is a deep neural network model, hybrid model. This is end-to-end model is between 2015 and 2020, and we are now in this era. They are called the speech foundation models. So that's a brief overview of the ASR part. Now we'll talk more about the challenges of language documentation. So we know that we always have very limited data resources for indigenous language, no matter in the States, in Canada, or in Africa. So for training ASR, we do need parallel corpora, which means like we need to align the text and the audio, and that is even more limited. So for contrast, like for mainstream languages, nowadays we can easily get public accessible, very huge data set containing more than 10,000 hours of audio and parallel text. But for indigenous language, we usually get like several hours or even less. So we also investigate later, like what happens if we only got 10 minutes of parallel speech and audio data. So the other thing is like, there is extensive vocabulary variations in most of the indigenous languages. So here are 2 examples. First is like my colleague is from Isagani-Geha. So like its nature makes its one word can represent the whole utterance in English. In that way, like we cannot expect many of the words we have to decode or have to transcribe, have those words, most of them will not be seen during the system training. So that's one of the key challenge. And the second one is kind of special for SENÇOTEN. It is called stress-driven metathesis. So this further adds to the complexity of the vocabulary. So for indigenous language documentation methodology, we can do it completely manually or completely automatic. But if we do everything from scratch, it takes a lot of time and effort. And if we completely rely on the machine, it is not reliable. Like we still need a semi-automatic approach, which we call it ASR-driven. So now I will go to our main contribution of the paper is the ASR-driven language documentation pipeline. So here is an overview of it. So like I just mentioned, I have little knowledge about SENÇOTEN, but of course my team does, but my personally, I don't have that much knowledge. So for building this system, we don't need to break the long words into subwords representations. I don't know how to like divide them. The only thing I do need is how to break the word into characters. So I do need to know the basic modeling unit. And that's all I need to know about the language. So it contains 4 stages. It looks maybe a little bit frightening, but the major stage is the latter 2. So for academic research, we have the first 2 stages to maximize the usage of all the data we have, but the major contribution of the performance improvement comes from the 3rd stage, which is like we actually conduct the cross-lingual transfer learning or just a fine-tuning of based on speech foundation models. And then stage 4 is to use the model for transcribing new audios. So I will go to this stage one by one. So the first 2 stages is for in-domain data augmentation. So our team have an expertise and a huge project on text-to-speech or TTS. So for the language, we do have some text-only data. So if we want to maximize the usage, we can try use the parallel audio and text data to train a specialized design TTS system first, then try to generate artificial or synthesized audio based on the text-only data. So the first stage is the training the TTS system. So later I will talk about our specially designed architecture and procedure to account for the limited availability of parallel data. So after we train the system, actually we provide a toolkit. It is open source. It is mostly done now. So here is the paper describing the toolkit, and here is the GitHub link. If you are interested, you can have a try. We have a very user-friendly interface to support the whole process. So after the system tries, it's like a speaker. It can take in text and speak it out. So we feed the text-only data and let the system to speak it out. So in this stage, we generate the synthesized audio. And for these 2 stages, we just want to augment the existing data corpora. If we don't do this stage, it's okay. We will see later, like they do bring performance improvement, but they are not the main contributor. So this is the main stage. It's actually, so we call it cross-lingual transfer learning based on the speech foundation model or SFM. But basically, we just like use the knowledge encoded in the parameters of the speech foundation models and add a simple linear layer on top of it and do a classification task. So each category is 1 character that is legible in the language. And after we do this, we call it cross-lingual transfer learning. We can finally use the fine-tuned speech foundation model to transcribe new audio without corresponding text. And to maximize the data usage in this process, we can optionally do language model fusion. Like we can use whatever part of the text, we can use some of them or all of them to create a language model. So for now, we only create a 4-gram language model which is a basic n-gram language model. But you can also create a neural network-based language model and try to let it in during the inference pass. So how this can be integrated? So for different architectures, we can do it either through shallow fusion or through unbiased hypothesis rescoring. And we will also examine its performance later. We can see that it can get us some improvement, but they are still not the major contributor. So like the first two stage, we talk about the TTS. So TTS is simply, if we put it on the high level, we input the text, we turn it into some representation, either in phoneme or character, and we train a feature prediction network, like turn the phoneme or map the phoneme with the Mel spectrogram, which is extracted from the audio. And another vocoder is like to turn the metro spectrogram, which we'll see later, it's like a picture, into waveform. It's listenable. So in our earlier work, we have a specially designed feature prediction network, which reduces the requirement of parallel audio and text data to train it. So more details can be found in this work. And we also do an additional part for the vocoder, which we call it vocoder matching. So first, we train vocoder, we use the ground truth Mel spectrogram and the corresponding speech waveform. But as we have little data, so the synthesized Mel spectrogram may be very different or have different patterns from the ground truth spectrogram. So after we train the vocoder, we can further use the synthesized Mel spectrogram generated by the feature prediction network and use the speech waveform as the label and to do a vocoder matching. And later we will also show its performance. So the last part, and also this is the most important part, is called the cross-lingual transfer learning. So our work differs from the previous one. It's like we try to properly incorporate the language model during this process. So this is an example that works for like Wave2Vec2, Hilbert, Data2Vec, and WaveLM. So for these 4 speech foundation models, they are encoder only before they are applied to downstream tasks. So we apply an additional linear layer. You can apply several, but we only apply one and try to classify it into characters. And then we can add the language model to during the decoding process. We call it shallow fusion. Like it is similar to a post correction, like a lookup table, but it is more complicated than that. Like if we have something that is very rare in the language model, then its probability will be turned down. So this is how the cross-lingual transfer learning works. So actually we use the pre-trained model parameters and add something on top of it, and use the parallel indigenous audio and text to fine-tune it. So now we'll talk about the performance evaluation, like how each part contributes to the process. So before that, we need to know what we have. So for this paper, we will work on the SENÇOTEN. So we have a data set from our project. It's the SGL project. So we have 4 hours of recording, but at the time we conduct the experiment, it is only, okay, I will be fast. 1 speaker, and after side stripping, we only have like a little bit more than 1 hour of audio, but we have some additional text. And we have language model, it's a smaller one trained on fewer text, larger one trained on more text. And this is the performance of the vocoder matching. We can see that it gives a better TTS system after vocoder matching. And this is how traditional hybrid ASR performs. We can see that it will fail for the unseen words. So that's the biggest challenge for indigenous language documentation with ASR. And this is how speech foundation model based ASR works. We can see that we try different architectures and different model size. And for the unseen word, the best one can get like around 45% correct. And if we further like incorporate the language model, it will give us some improvement. But incorporating a language model may lead to performance degradation on the unseen words, like it may not always help. And later we have the language model fusion with the data augmentation, like we have some augment data. And we can see that the augment data can give some performance improvement, but that's not that much. After language model fusion, still gives some more. And the best system, like it gets nearly 95% of the characters correct. And if we ignore some easily correctable errors, like we can have an overall word error rate of less than 15. So remember, like almost more than half of the words in the test set are not seen in the training set. So we also have some ablation studies, like if we only have 10 minutes of data, what will look, it still helps. And the last thing I want to show is like we have a user interface to support the usage by the community. So if you use our model, you don't need to know any specific programming language. You just need to click the button, record your audio, upload it, and we'll give you the result. And everything can be protected under an encrypted link. So nothing will be released. We try our best to protect it. And we are looking for collaboration. Thank you. So
yeah, we'll cut in. So we'll cut into the break. 5 minutes for questions. We'll start the next one, maybe 5 minutes for questions and start a little bit later. Okay.